Now, I look at this and I find it a little bit awkward. Okay, I'll tell you why I find it awkward. Let's think back to the normal derivatives you're used to. Okay, a normal derivative from a normal function. Okay, something like this. You know, I don't know. Okay, there's a normal function. Okay, and you differentiate it, and what would you get? No, seriously, what would you get? 3x squared minus 12x cubed plus 1 constant. Okay, good. Okay, no problems. Okay, now have a look at this with me. You have a derivative, a rate of change. Okay, what's it in terms of? It's in terms of x. It's in terms of the input. That makes sense. Your original function was in terms of input, so your derivative, your rate of change, is also in terms of the input, right? But what do you have down here? This is weird. This looks a little bit like what we get out of sort of like implicit differentiation sometimes, but usually like those variables are mixed. This is unusual because I have a rate of change not in terms of the input time, but in terms of the output, h. It's kind of weird. I mean, it's still true. We drew some conclusions from it, and it makes sense of what we observed. But it's a bit weird. It's a little bit weird. Okay. So my question to you is, can we get this in terms of time? Can you get it in terms of time? Now before I show it to you, I want you to have a think about it. I want you to try on your own steam. Can you get an expression for dh on dt that's not in terms of h, that's in terms of time? Could you work it out? I'll give you a few minutes to have a think about it. I'll leave all that information on the board. Give it a go. Let's give this a go. Remember I told you, you have to think about what you know about this and bring it to bear onto this. Okay, and that is hard. It's conceptually hard. Okay, so let me walk you through a little bit and hold your hand. Okay, we've been talking about derivatives, haven't we? All these rates of change and so on. Okay, but derivatives are only half of what you know about calculus, aren't they? It's only half. What's the other half of calculus? It's integration, isn't it? Now, admittedly, this is making a leap, but stay with me. Okay, we know this. We know that. Okay? So, logic ought to tell you that you can take that statement and turn it into another statement through integration. Now, here's the reason why I'm going in that direction. Okay? I want some relationship between dh and dt, right? But I don't want it in terms of h. I want it back in terms of t. What's the thing that connects h and v and t? And the answer is, it's back up here. It's volume. Volume connects the height and the, what am I looking at? And time, right? So that's why I'm coming back to this step, right? That's why I've gone here. It's not just arbitrary, like, let me just pick an equation and see what I can do with it. I picked this one because if I can express time and volume together, I can get to height. Okay, so watch, right? What statement could you make out of this differential statement, differential equation? What would you make in terms of integration? What could you say? You'd integrate both sides with respect to t. Now, by the way, we've been so used to just saying integrate, right? And we don't have to care about what we're integrating with respect to. But can you see, it is vitally important that you think about what you're integrating with respect to, because you can integrate with respect to anything, okay? Any variable, I should say. So, therefore, you get v on this side. What do you get on the right-hand side if you integrate with respect to t? 180t. But I haven't given you a domain, so you have a constant, don't you? Oops. Okay. Now, ordinarily constants are a bit of pain, aren't they? Okay. But you have enough information to get rid of that constant, don't you? Or at least to work out what it is. What is t? It's time. It's when I started pouring, I guess, right? So therefore, you know what the volume of water is when I started pouring, when t equals 0. What volume of water was there? 0. There was no water in there, so the volume is 0. So when t equals 0, v equals 0, right? Therefore, 0 equals 180 lots of 0 plus c, so there's our constant. Now, you are used to thinking about this in terms of, oh, here's a derivative, and it passes through some function, and the function, right, it passes through some point, I don't know, 1, 3, or something like that. So you take an x and a y, and you stick them into your expression, right, for your indefinite integral, and then you evaluate C, right? But all of this is just talking about real things like time and volume, okay? It just so happens that we call them X and Y because we're thinking about abstract situations. But these are not abstract. You just need some information like a point in space or like a volume at a time, and you can work out a constant. So, I have this. Yes? Okay. Now, can you see now? This is my bridge. This is my connection between height and time. I want to get out of, in terms of height, I want to get in terms of time. What can I do here? I know what the volume is, don't I? This is the volume. That's the volume, right? So I can say a 12th pi h cubed, that's 180 t. This is all okay. This is a thing that's changing. It's the volume of water in the cone at any given time, right, in the glass. That's changing. This is changing too as time goes on, right? What did I want? I wanted dH on dt, didn't I? So I need h in terms of t. Let's do it. What do I get? H cubed. What's 18 times 12? I have no idea, actually. It's 144 plus 72. What's that? Is that 216? 216? So 2160 t over pi. Does that look right? Did I get rid of all of the constants on that side? I did, didn't I? Okay. Now we've been very careful about taking the square roots of both sides, haven't we? Because it introduces all kinds of problems with sign. Okay. But there are no problems here, are there? No problems because I'm not taking the square root. I'm taking the cube root. I have no problems with that because the cube root is, this is a function, right? Cubing, right, and taking the cube root. They are exactly functions and inverse functions of each other, unlike the square and the square root, okay? Thanks a lot, volume. Okay, there we go. There's h, which is, 2160t on pi to the power of a third. So you could differentiate this, couldn't you? And off you go, you get your dH on dt, and it's all in terms of t. That's really cool, okay? Now you can go ahead and do that, but I'm just gonna go off this, because I can draw another graph now. What graph could I draw? What should my axes be? What would you choose? Vertical axis? I should probably make that the output, shouldn't I? H, right? So that makes my horizontal axis time. So I'm thinking about how the height changes as time progresses. Yes? Tell me, what does this look like? The 2160 and the pi, can you see they don't really matter? Not really. What do they change about this graph? They change its steepness or its scale, if you like. They're not going to change the basic shape, okay? So if I just think about this cube root and the t, what's that going to look like? Think about your inverse functions. If you thought about x cubed, it looks like this, right? So therefore the cube root of x, if you do your reflection across y equals x, what's it going to look like? It's going to look like this guy. Okay? So that's the cube root of x. Now, I only want part of it, don't I? Because we've noticed some restrictions on the domain, haven't we? Okay. When time's 0, what is the height? It's 0. So I'm at the origin. Unlike this guy, he's not defined there, okay? But this guy is. What does the rest of it look like? We'll have a look at the rest of the shape. It's going to look something like this. Okay? Does this match what happened? The height of the water was increasing, but it was slowing down as time went on. Okay? Now, that looks pretty good. Shape looks good. There's something wrong with my graph. The same thing that was wrong before, right? This graph, just like that one, it has a boundary. It has the same boundary that this one has. It just so happens it's on a different axis, isn't it? Okay? So I should end at some point when h is 24. Now, just because of the observations that we made approximately, you actually also know the endpoint for this axis too, don't you? What is it? It's 20, because that's when we said the water got to the top and I kept pointing, but the water in the glass didn't change. Okay?